Hello, community. So great to see you. We talk about NVIDIA. NVIDIA has some beautiful new models that will fit your GPU VRAM limitations. Let's talk about the latest Nemotron elastic AI architecture. Welcome to my channel Discover AI, where we discuss the latest research paper. Now, researchers at NVIDIA successfully trained here a 12 billion parameter reasoning model. But there's a twist. That single training run also produced a 9 billion model and a 6 billion reasoning model. You might say, hey, this is not possible, no? We trained those models separately on their own dataset. And now NVIDIA is trying to bring all together into one. So usually, you know what we do when we need a smaller model here for edge deployment. We either prune it and we have massive retraining costs because we have to heal the damage done by the pruning, or we simply do here a student-teacher model and we train here a student model from scratch. Beautiful. But if NVIDIA is trying now for their data center AI models, but also for your customer GPU models, to integrate multiple models into one model, there is an advantage. So, but what if the 6B model you need is not a separate entity? What if the 6B model is already inside the 12B model, waiting just to be carved out like a statue here from marble with Leonardo da Vinci's David? They did it. Okay, Nemotron Elastic. A fascinating paper. Nobody's talking about it, but I love it. Let me explain why. We are here, November 21st, 2025, Nemotron Elastic. Efficient many-in-one reasoning LLMs. You know, we have here the normal LLMs, then we have a mixture of expert elements, and now NVIDIA is trying to come up with a complete new elastic AI architecture I found impressive. So to further improve here the beauty of my channel, I built here an interactive visualization for you so you clearly see what is the difference between a mixture of expert model here on the left side and the Nemotron elastic model here on the right side. Please have a look here at the VRAM load. So here you need 48 gigabytes, and here, let's say with this publication, we have a model with 12 gigabytes. You know, mixture of expert, you can have multiple experts. Let's say one expert is in theoretical physics, the expert is in mathematics, the next expert is in chemistry, in medical. You get the idea. So have a look at the active parameters, 6 billion parameter, and the total parameters are 47 billion. So the expert loaded, but idle taking up space. So if I increase now the number of experts here, you see I target now expert 1 and expert 2 with the complexity of my query. And I can increase this, and you see the numbers go up. Now we are active parameters at 24 billion parameter model. Total parameters are 47B. And it is the same VRAM load, 48 gigabytes. And guess what? The more experts are activated, the more I have now access to general interdisciplinary scientific knowledge. You see all the experts, 7 experts are now working. I have now an active parameter model with 42 billion pre-trainable parameter. The total parameter stays the same, 47B. And of course, the VRAM load is, as always, 48 gigabyte. So you see, you have to download a huge model, even if, let's say, your complexity is would theoretically only need 3 experts. And now NVIDIA is saying, hey, let's improve this. Here again, the VRAM load is 12 GB. And the active parameter model is 6 billion parameter model. And the total parameter is also 6B. The unused weights for a particular model are physically unloaded. You don't download the complete, let's say, like here, 48 gigabyte, but you also download here a real smaller model with an elastic target deployment. So let's have a look. If you have a simple question, you only need here the 6 billion free trainable parameter model. Ne? But let's see if we increase here. Let's say we go now to a 9 billion. So you see, active parameters 9 billion, total parameters 9 billion that you download this model, and your VRAM load is now at 18. So you increase from 12 to 18. And if you have a real powerful customer GPU, you can go even higher. Now you have here a 12 billion model that you can download with full 12 billion parameters, and the VRAM load is now 24 gigabytes. So you could now have a selector here by NVIDIA sees what is your customer graphic card, or if you're in a data center, what is the configuration available in a data center, and choose here for the maximum performance here your different configuration, your different model size. So you see, this is now huge because for a 6B model, you only have not like a mixture of expert to download the full one, but only a tiny little model size. What a nice innovation by NVIDIA. And you know what? They integrate a Member 2 block plus multi-layer perceptron plus transformer architecture. Let's have a look. You can have this already today here on Hugging Face here. You need to agree to share your contact information. There's some heavy licensing on it, okay? But I want to draw your attention to two things. At first, the downloads in the last month was 33. Not really a lot of, so the community is ignoring it. But the second is the tensor type is a B-float 16. Now, this is interesting. Let's say, what is going on here? Let me explain. So I just want to show you in this interactive representation what we are talking about. So we are talking about Nemotron Elastic, the layer importance ranking. So let's start here with the 6B core, the highest importance layer. This is the spine here of the logic engine if you want. So what they do, let's say we have a system from L1 to L20 layers. And now, given here a particular pre-training, a particular pre-training data set here, the routine, they now assign here particular importance values to particular layers. Let's say you're training here on a pure abstract mathematical data set in the pre-training. So beautiful, and you can identify what is the importance of each layer. So to do this, and you see layer 20 has an importance of 90%, 19 of 95%. And so they identify here the layers that are above, I don't know, let's say 80%. Is that about right? Yeah, seems about right. No? So those are the primary logic layer for your particular pre-trained task. If you go then and ask something about biology, this will be a catastrophe. It will fail. This is not going to work. So we are highly focused, domain-specific pre-training data configuration. Great. And then you say, okay, let's go now to a 9B model. So we add now for the importance here, the models that are refining now, giving more causal reasoning to it. So this 9B model, great. Now you see those are the layers that are trained. But of course, if you want to have the full reasoning capacity of a 12 billion model, a Member 2 plus an MLP plus a transformer architecture, now we also have here the fine details that we can add. And now we see layer 1 to layer 20 is now activated. But you have now an indication here, especially for your particular training set, what is the core layer in green? What are now the refinement layer in pink? And what are just the detail layer that we need if you really want to go into have a question about details? If you just have a basic question, the core layer might be enough for you. So the router can now train and decide which of the model here are optimized for your particular complexity in the query. So I hope this gives you here a very easy instruction. Let's just talk about the last one, the accuracy. Now, NVIDIA, and this is the real data here, for the Nemotron Elastic for their 6B model, they give here 4 particular benchmarks, as you see in the study, reasoning accuracy in total overall about 70%. So they say for our 6B active parameter model, this is it. And this is great. If you go to the 9B, they reach 76%. So you see, okay, we have refinement layer that are now additionally activated. But of course, if you go to a 12B model, you can reach, and you see we are saturating on a plateau, 77.4%. I hope this gives you here a small indication in this interactive graph here, how this model works. Coming back to the video. So you see our Elastic 12B model is an LLM deployed here by NVIDIA only for research purposes. It uses here hybrid architecture. We have a Member 2 blocks, and we have MLP layers combined with attention layers from the transformer architecture. And they only have 4 attention layers, and you will immediately see why they try to keep it simple. They design it to enable here elastic inference to nested model extraction. Let's have a look. If you want to know the base model, it is a Nemotron Nano 12B version 2 incorporated for advanced reasoning capabilities. And now you know why my channel covers this, optimized for mathematical and scientific reasoning tasks. So if you work in science, this is a model you should be watching out for. And yeah, Hugging Face NVIDIA, you have everything available for you. You can try it out, no problem. But let's understand here the main new idea, and they have some brand new innovations. For NVIDIA as a company, of course, for the data center, it is essential to reduce here the cost and find AI models, new AI models, like this one that achieves a 7.2 times reduction in the training tokens compared to all the traditional compression methods that we apply currently in AI. Plus, a 42 memory reduction compared here to normal 9B and 12B checkpoints. 7.2 times reduction for the tokens and 42% memory reduction. Now you understand why NVIDIA is building its own models. Interestingly, all of those models and submodels share here the weight tensors with the parent models. And now hold on to your socks, because this is gonna be amazing. It can be extracted zero shot during the deployment phase without additional training or fine-tuning. So if NVIDIA manages here to build one huge impressive model, all the little child models can be extracted in a zero shot, no training, no fine-tuning, no nothing. And it can be automatically optimized for your customer GPU, for your NVIDIA GPU with 2432 gigabytes of RAM at home. How they did it? Here we come now to the interesting part. They designed a group-aware SMM elastification for the member 2 blocks that preserves here the structural complaint of the member. For the MLP board, they have also some elastification I'm going to show you. Plus, and this is really nice here for the transformer part here, they have normalized MSE-based layer importance for an improved depth selection. Plus, a knowledge distillation enabling a simultaneous multi-budget optimization. A lot of new stuff to explain. But I think the core claim of this new paper is that we can delete entire layers from a reasoning model. You can have a member head just deleted, cut off, or MLP compressed, or transformer layers just deleted out of existence if you need a smaller model. And you might say, no, this is not possible. It's a dense network. You cannot just delete heads or layers or neurons. This is not possible, because the model will hallucinate or simply crash, no? And you might say, how they made this possible? How is this mathematically, technically possible? Let's have a look. It took me quite some time, and I'm not gonna present you the paper by NVIDIA. Go read the paper, try to understand it, then come back, because I give you now my personal reflection on this paper, and I give you a simpler explanation. It is the magic, if you want, they activate a residual stream much more powerful. Now, you know that modern architecture, AI, whether a transformer or hybrid member blocks, do not process the data sequentially through the layers like y equal here a function of x. They process the data in addition. No? You have x for incoming and a layer x of incoming. Beautiful. And you know what? This is the secret to the elasticity idea. Now, the residual stream act as a superhighway. These skip connections that we already had for years in our transformer are now repurposed. So those layers are merely now off-ramps that process data and merge it back in. So when the Nemotron elastic router, whatever you like, decides that, for example, layer 5 is unnecessary, if you only have a small NVIDIA GPU at home or a data center is at its maximum performance, peak performance, it needs to reduce the model. It can do this because it just decides to cut here the layer 5 of the model. Mathematically, the layer becomes here simply 0. The equation collapses here, as I showed you, to an identity function. Yeah? So the data flows now seamlessly from layer 4 to layer 6 across the residual bridge. So we took care about the computational connectivity problem. So there's no gap in the tensor shape, in the weight tensor shape that we can calculate it. But semantically, we have a huge problem, no? So structurally, the tensor fits. But layer 6 expected here a highly processed feature input from layer 5. I mean, this is the reason we have layer 5. And if we suddenly feed it the raw features from the layer 4, just in this example, the layer 6 should output just garbage. And this is why all our standard pruning technology requires additional fine-tuning. We have to fine-tune the model again. Now, Nemotron Elastic solves this during the pre-training phase. They found a new idea and they call it stochastic elasticity. Remember, this is now a hybrid, a Member 2, an MLP and a transformer architecture. So they show us, hey, we can do this not only on each of those three components from Member to transformer, but we can also do it here on a hybrid system. But it involves massive pre-training. But if you are NVIDIA, who cares about compute infrastructure? So during the training, this learnable router, optimized via a special Gumbel softmix function, real nice, randomly toggles now the layers on and off. And this happens thousands of times during the training phase. So let me give you an example. In step 1, the layer 5 is active. So the layer 6 learns to process the level 5 features that are coming in from layer 5. In step 2, the layer 5 is skipped. Now the layer 6 is forced to accept a level 4 feature directly. And if you switch on and off all possible combinations of all possible layer switching and layer deleting and whatever, you have a new training pattern. So if you want, this forces here the tensor weights here of layer 6 to become more polyglot or bilingual or multilingual. So just here they become robust to varying levels of input abstractions. So this happens in the pre-training data. You can't do this afterwards. Now, I've seen that the first comments go about a self-healing network. And you know this is nonsense. A network cannot self-heal itself at runtime because it was trained in the pre-training phase to learn here different input patterns. Patterns, okay, yeah, forget about it. So it's not just about skipping layers here, the depth of the architecture, but it is also shrinking here in the width. And you say, my goodness, how this is gonna happen? Well, NVIDIA here pulled out here all stops here, and they say, okay, if we think about, AI is more or less just a multiplication of some tensor structure, matrix structures, whatever you see it, no? So let's say in the simplest example, if we have a weight matrix W of the size 4K times 4K, the 6B model now uses a specific subset, the strict top left submatrix of the size 3K, 3K. It builds this in the pre-training phase that the most important neurons are located now over there. So if we say the 6B model is inside the 9B model, we literally mean this. Yeah, absolutely. In the term here of our tensor structure, this is exactly what's happening. So if we have a weight matrix here, 4K, 4K, got it. The algorithm uses now normalized mean square error to rank the importance of every neuron in the pre-training. So the most critical neurons for a particular pre-training data set. Let's say you train on simple mathematical problems, then a little bit on more complex mathematical problems, and then on theoretical physics challenges. For those particular tasks, the importance of every neuron is evaluated, noted, and will become a part of this elasticity optimization. And guess what? As I already indicated, the most critical neurons that are now sorted, given their importance, given the pre-training learning, they are now sorted to the top left indices of our tensors. Now this creates a beautiful hierarchy from a mathematical point of view, né? Because the 6B core, if you want, it's the spine of the logic. No? These are the absolute most critical weights that we have to have if this model should do anything at all. And the 9B, think about a human brain, the cortex, contains now the core plus the refinement weights. And the 12B here is everything, the full brain, everything plus the tail weights that handle here some nuances or some really important details. So the 9B model doesn't pick different weights than the 6B. I've read this also somewhere. It just picks more weights. In addition, it picks more weights up to increase its reasoning. But you might say, how the hell are we going to train this? In one run? Are you joking? We have to mask layers, we have to mask Mamba heads, we have to compress MLPs, and now we have to do this in a matrix multiplication? Well, NVIDIA, it seems that they managed. Now think about this. Normally what we have, let's say chain of thought. I only have about 100 videos about chain of thought. So they need, let's say, just 1,000 of tokens. And the researcher found that if they sample the budgets uniformly, so train here the 6B, 9B, and 12 equally, the gradient updates from the struggling small models overwhelmed now the fine-tuning of the larger models. And this had a simple effect that we know that the 12B model just became more stupid. So we have exactly the opposite of what we wanted to achieve. So what is the solution? What can we do? NVIDIA found a solution. They call it a two-stage curriculum training. So let's have a look. Stage 1, for the shorter context, they say, okay, 8K sequence length, and we use a uniform sampling. Yeah? Let the router stabilize the AI architecture. Just think about this sentence. This is a real powerful new idea. But then, of course, you have to implement the reasoning phase. Because if you do science, you're not just with short context. No? So ramp up, NVIDIA did it here to 49K sequence length. And now comes the magic, the beauty, whatever you want to call it. They have now a particular sampling probability that they imply for these three different models. Look, for the 12B model, it is half. For the 9B, 1/3. And here for the 6B, it is 20%. Now why? Think about it. If you have this Matryoshka principle here, the Russian doll principle, they all use the same inner core tensor structures. So by prioritizing now the 12B model during a complex reasoning phase for a scientific task, they allow now the smaller models to draft off the high quality gradients of the parent models. And this curriculum, the NVIDIA tells us, is the only reason the 6B model can handle already a little bit of complex math without breaking here a chain of thought. So what we achieve is the 12B model doesn't get more stupid, more dumb, but more intelligent. And the 6B model is, how do you say this? Utilize it, the training of the 12B model, because at the core of the 12B model is the 6B model with the identical tensor weights. And now those tensor weights in 50% of all the training cases are also trained. You see this idea? So simple, but so beautiful. If you read it the first time, it happened to me. I said, I do not really understand how this is going to happen on a mathematical framework. Can you write down the mathematics for me that I can code this? Now, then I had a second look. So by forcing now the training loop to select here the 12B model 50% of the time, as I just showed you, so we are letting the full brain handle the difficult reasoning data, okay? So the full model looks here at the hard reasoning task. It has more layers, it has more neurons, it has a better pre-training data set, it has a higher complexity level that it can handle. Let's say it understands the logic. So it calculates now a higher quality gradient structure, a more precise adjustment here for the tensor weights. But the 12B model updates here the core weights that also the 6B model uses. No? So when the 12B model does a backpropagation update, what happens? It tunes here the outer neurons, so also the 12B exclusive neurons in all Number 2, MLP, and transformer architecture. But of course, it also tunes the inner neurons, the 6B core. So even if the 6B configuration wasn't active during this particular step, its weight got improved anyway because they used the same tensor structure and really the same identical weights. So it drafted behind the 12B model. The 12B model smoothed out here the path of the 6B, fixing here the core logic in a way that the 6B model would have never done on its own. It doesn't have this complexity to understand this. So interestingly, we improved the 6B model with the logic of a 12B model because they have the same core weight structure. What an elegant methodology to train the 12B, the 9B, and the 6B model in one run. In one real complex run. No mistake. but in one run. So by prioritizing the 12B model in our pre-training process, we ensure that the shared weights are optimized by the smartest intelligence available, our 12B model, preventing here the dumb configuration from corrupting here the shared brain like it happened until now for all our training exercises. So let's have a look at this training loop. This is my understanding, and if I'm wrong, please correct me in the comments. So we have a shape-shifting training loop for this new Nemotron elastic with number 2 MLP and transformer. Let's have a single run with 1000 steps. Let's start simple. So we have a batch of data arrives here, a math problem, and let's say the router makes a decision, hey, let's do the 12B model. Model activates all the parameters exactly like a normal 12B model. And the result is the weights get smarter for high-level reasoning. Now at the second step, now the system decides to train the 6B model. Now the system applies here particular masks. It temporarily blinds here the outer layers and the model becomes now a 6B version. Now for the distillation, for the knowledge distillation, we have a critical link, no? We have to run the 12B teacher model, which is the full model on mask, because we want here to have here the correct answer, the high complexity answer that a smaller model cannot achieve, and what the answer should look like. And then we run the 6B student model, mask, runs the data and tries here to guess here the result. But when we do here the optimization, so the updates of the shared weights, we do it in a way that the 6B student the weights look more like the 12B teacher models. So we do have a 6B run, but after this run, we have another optimizer looking at this and say, come on, let's nudge your 6B weights a little bit more to your 12B teacher weights, because, you know, this is the solution that we are looking for. And because the 6B weights are physically located inside the 12B weights, every time you update here the 6B model in step 2, you also are partially training the 12B model, since the 12B model uses these tensor weights too. I like the idea. Now let's come back to the simpler cases here. NVIDIA uses here particular precision at 2 bytes per parameter, a 16-bit precision, and they use here bfloat 16, a 16B format. Why no quantization? I normally go with an 8-bit quantization, but they went here with 16-bit. Why? Why did NVIDIA do this? Now they tell us here in high-stake reasoning, research, chain of thought capabilities, benchmark testing, math testing here, AIM 2425, the researcher avoid the quantization during the study because the quantization introduces rounding errors. And normally the rounding errors, we have methodologies to somehow have an error prediction code for the quantization quality reduction that we introduce. But now the model is performing a quite intensive pre-training. If you perform a delicate, just only go with 50-step logical deduction. Even the tiniest rounding error in step 10 can have a cascade effect into a hallucination by the step it reaches 40. So NVIDIA decided here to have a good performance on their 6B Nemotron elastic model. They went with a 16-bit, a bfloat 16 data structure, isolate the variable to prove that their elastic architecture work without the noise of the quantization artifacts to take care or try to optimize for quantization. So at first they have to prove, hey, it is working. But since they themselves, and I know they also go here with an 8-bit architecture, that they stick to a 16-bit architecture is a clear indication that all the complexity of the matrix multiplication, they need this precision. So this is now interesting because on the one side, they try to bring here the model size down, but they tell us, hey, to achieve the quality of the output, at least for this research phase, they went with a 16-bit encoding. NVIDIA tells us they choose the 2 bytes because this is the Goldilocks zone. So it is small enough to fit in memory, but precise enough not to make the model stupid. Given this should be a science model, or at least a model that has a capability to solve some more complex reasoning. So just to give you an idea, if we have the 4 bytes, if you go with a full FP32, you have, for example, this standard precision, takes about 48 gigabytes for a 12B model. Then NVIDIA went here with this variant, but of course you can go down to a 1 byte to an integer 8, where you have a very low precision, but the benefit is it takes only 12 gigabytes, so maybe it will fit here on your or on my customer GPU card. But very low precision. Given the complexity we're doing right now, this is no way, and NVIDIA decided here to go with the Goldilocks zone. Interesting, not an 8-bit, but a 16-bit, so careful. Yeah. Also meets nicely, I think, that quite some NVIDIA customer GPU have a 24 gigabyte VRAM. So this model here, specific Nemotron Elastic, would run on 24 gigabytes or 32 gigabytes cards. So it comes down to the, let's say, customer AI clientele or even small and medium enterprises. Let's be clear, an elastic AI architecture is something beautiful and is something real challenging. And I think this was real interesting, this paper. Because by designing a new AI architecture to be elastic, and you see we used here quite some new innovation, residual highways, submatrix sampling, curriculum-based routing, NVIDIA can create here really a single artifact, a single LLM that adapts to the hardware of the user if you only have 24 gigabytes of RAM. So, if you want, short summary of the innovation, we have a structural innovation, a semantic innovation, and a dimensional innovation. Structural is the residual stream, removing a layer of an architecture, simply turns it into identity function, and using here the residual stream, we can work with this. The stochastic training ensures that the layer n+1, 6, is not confused when it sees now n-1 output. So we can have these skipping connections. And for the dimensionality, for the reduced dimensionality, the ordered slicing ensures we always multiply compatible submatrices. The top left corner, this will become really interesting if we go then to our typical low rank adaptation, but more about this in the following videos. If you read this paper, have a look. I think what's also beautifully done is the Mamba2 layer group aware elastification methodology. Because you cannot simply randomly delete neurons in a Mamba layer like you can maybe do in a transformer, because Mamba2 relies on a strict group state space model on a structure here for their hardware efficiency. So if you break the group alignment, all the CUDA kernels here would just fail. All the computational instructions are gone. So, of course, NVIDIA is the best place to optimize here for fast CUDA kernels. And I think they really done it in a really nice way. They invented here a group-aware masking technology. So the router it's rather simple. The router is forced to apply a block mask, and it can turn off an entire head, or it can turn off specific channels uniformly across all heads in a particular group. And NVIDIA shows, hey, it is working. So real nice details. So if you want to learn about new, emerging, upcoming, flexible, elastic AI architecture, without any quantization, I want to underline this. This is really heavy scientific stuff. This is not for the social media AI thing. This is really science AI. This is an absolute fascinating view into the future. If you are not sure about Mamba, you want to learn about it, for me it's a year ago. I have multiple videos on my channel, Mamba AI S6. Then I optimize and fine-tune a Mamba S6 with a DPO alignment. Here we go through the code. If you are a little bit more into mathematics and want to go beyond the mathematics of a Mamba S6 into vector fields, I have here this particular video. My goodness, 1 hour. Okay, for you. Or if you go here into hybrid Mamba transformer architectures, this is the video for you. Or especially if you're interested in Blackwell tensor cores, we have a Mamba model with meta tokens here. 11 months ago, I did here the models here on meta tokens, NVIDIA Mamba models. So there's a lot of new information out there. They are trying to build new AI models. They see it's not working. But of course, what's also out there is the beauty here of the TPU innovation that happened here on their infrastructure here, especially with Google and with Gemini 3 Pro. And maybe this will be here a detailed upcoming video if you want to learn more about the complete other side of NVIDIA, about TPU architecture. I hope you liked it. Maybe you subscribe, maybe you become a member of my channel. Anyway, I hope to see you in my next video.